everybody. So, the aim of this work is to investigate the crack propagation path in planet gears for aerospace applications. This investigation has been done by simulation with extended finite element models, and this work is a little part of a wider research aiming the investigation of the crack propagation in lightweight gears. So, planet gears for aerospace application are usually supported by roller bearings, and a planet gear respect to a standard gear has two tip pairs in contact in the same time, so we have a different loading condition. Moreover, the outer race of the bearings is created on the gear hub, so this creates a different clamping condition respect to standard gears. Thin ring gears or lightweight gears, as you want to call, are geometrically identified by two main parameters that are the ring thickness, given as the backup ratio, that is the ratio between the ring thickness and the modulus or the height, and the web thickness, given by the web ratio, that is the ratio between the web thickness and the phase width. So this is a general thin ring gear. In planet gears we don't have the web, so we define the planet gear just with the backup ratio. The problem in lightweight gears that are mainly used in aerospace application, but they find application also in automotive field, in particular in new electric cars, has this kind of problem because the rim is thick. If a crack nucleates, it can propagate mainly in two directions. One in the tooth direction and the other is in the rim direction. If the crack propagates through the tooth, we have a so-called safe failure, because if the rim is, if the tooth is removed, the consequence is not so dangerous as it happens if the crack propagates through the rim, because we have big portion of the wheel that are thrown away. So if we want to perform a safe fail design, we want that if a crack nucleates, the crack must propagate only through the tooth. The crack propagation direction is not deeply investigated in the literature, and the most important works are those carried on by the NASA, because they did the only experimental results that we can find about this problem. And from the NASA's works and other works in the literature, we can identify three zones of backup ratio variation. The first zone is called the safe zone. So for values of backup ratio higher than a threshold, we have always a propagation through the tooth, so a safe propagation. If the backup ratio is lower than another threshold, we have always a propagation through the rim, so this is a dangerous zone. And then we have an indetermination range. Indetermination because in this range of backup ratio, the cracks may propagate through the tooth or through the rim according to other parameters, such as the crack initiation point, the speed, the web ratio. In this work we performed only numerical simulation by means of extended finite element models. We started the investigation with the three-dimensional models, and then we shifted on two-dimensional models. The approximation of these models is mainly due to the simulation of the rolling elements, because we used simply sliders to simulate the roller bearings. Then to see the effect of the crack initiation point, we nucleated the crack in 4 different points. The first is the point where the maximum equivalent stress is reached, and then we take 2 points up and 1 point down. So firstly we used the three-dimensional simulation. From this simulation we inserted a crack in the middle of the face width and on one side of the face width. From this simulation we appreciated that the crack first propagate along the face width direction and then on the tooth or rim direction. And this is also justified by the stress intensity factor calculation. So the stress intensity factor is always higher in the lateral side of the initial crack. So we concluded that the propagation in the face width direction is not so interesting, so we used just two-dimensional models that are less time consuming. And so the main results are divided in two. The first are propagation with low speed, so propagation with negligible centrifugal load. In this case, we can see that for backup ratio higher than 0.6, we have always safe propagations, so propagation through the tooth, and for backup ratio lower than 0.6, we may have propagation through the tooth or through the rim according to the starting position of the crack. Then we added a not negligible speed up to 10,000 RPM, and we noticed that for a test case, for this one with backup ratio 0.4, the crack propagation changed direction from safe from through the tooth to through the rim. In the other case, we noticed a certain changing on the crack direction, but the changing was not enough to change the direction. Comparing the result of planet gears respect to standard thin ring gears, it is interesting to appreciate that the limits where the propagation is safe is lower. This means that we can create gears with lower thickness and so lighter gears. Generally speaking, we find out that as in standard thin ring gears, the crack propagation direction is influenced by the ring thickness and the crack initiation point, but the limit in backup ratio is lower than in standard thin ring gears. So if the results will be validated by further simulation and hopefully more accurate simulation with the right contact between rolling elements and bearing trace, validate this, it will be possible to design lighter planet gears. And to conclude, it would be also nice to do also experimental tests, but this is the most expensive activity, so for the moment we have to consider just simulations. Okay, so I finished. Thank you.